All right, I'm going to reintroduce to you the phenomenal Ms. Michelle Gabiro in a moment, because she is going to be our first speaker, of course, joined by Christelle Simuerey, who is the first time FGLer. We're so excited that both these ladies have decided to join us today. They could have been doing anything else on a Saturday, but they're here to help you sharpen your excellence in the periodic table. And Ms. Michelle Gabiro is a distinguished mining geologist with a Masters of Science in Mining Geology obtained from the University of Exeter at the Cumberland School of Mines out in the UK. She also obtained a BSc Honours in Geology from the University of Brighton, also out in the UK. She has expertise in managing underground and open pit projects, production ore control, leading drilling campaigns, and is currently a senior reconciliation geologist at Kibali Gold Mine, DRC Barrick Gold, where she is in charge of reconciliation and balancing the books in terms of answers and lots of other things. Michelle was an exploration geologist at Koniambo Nickel and KNS Glencore, New Caledonia before that, and she led the introduction and the management of the very first helicopter drilling campaign on site, coordinating performance tracking and ensuring a safe project execution. She's also implemented long-term budget plans to optimize the exploration plans with efficiency and higher productivity. She's a superstar who has a job that has her globe trotting the world, but also really experiencing the beauties and the wonders of mining geology. Michelle, good morning, afternoon rather. Welcome back to FGL. It's so good to have you back with us.
Thank you. It's good to be back. I really appreciate the introduction. It's a warm welcome.
We are so excited, and thank you for bringing along your colleague for today. We're so excited to also have Mrs. Christelle Simuerey, who has a Bachelor of Science in Industrial Chemistry at the Kampala International University of Uganda. She obtained that in 2016. She is a laboratory metallurgist responsible for geometallurgy in the process plant at Kibali Gold Mines, where she works with Michelle, a laboratory technician in the process plant at Kibali Gold Mines from 2016 until 2017 before she took on this current role. And before that, she was also a junior metallurgical statistician in the process plant at Kibali Gold Mines from 2017 to 2020. A summary of her many roles includes generating a geometallurgical database for all future feed sources, providing prediction of material response. She develops and proposes and optimizes effective processing route for all future feed management. Also, she assists in designing and evaluating circuit improvements. She conducts plant performance data analysis linked to feed blend for productive action, and also complies, of course, with health, safety, security, and housekeeping standards in the work environment, as she provides lab input and board reporting and preparation. So really an integral part of the cog there. And also it's our first time ever having a metallurgist here join us at FGL. So we're super excited. This is Christelle. Hello, are you there? Welcome to Future Global Leaders Club.
Yo, thank you. Thank you, Oluwetu. Thank you so much. And I'm glad to be part of this club. This is an amazing group, and I'm very happy.
We are so thrilled. And we can't see your face. Perhaps you could turn on. There you are. Yes. And there you are. A really incredible profile. We are so excited to have you unpack and dive into the world of chemistry, the world of the periodic table. I'm going to hand it over to you and Michelle. FGLers, I want you to really engage in this session. And there are lots of points where it's going to be an interactive session where you're interacting with these brilliant minds that are coming from all over the world and are here to particularly serve you in making sure that you embed your knowledge and understanding in the periodic table. So questions in the chat box. If you have a question during the interactive section, put your hand up. With Sandy and we're going to identify you and you can interact with some brilliant minds. I'm going to hand over to you, ladies.
Yeah. Fantastic. Thank you so much. Okay, so I'll start by sharing my screen. So if you just bear with me one moment. And please give me a shout if you can see.
Perfect.
Yes, we can see.
Fabulous. Okay, so I'll start by introducing the periodic table, just how magical it is. It's part of our lives, so just tune in. Anytime you have any questions, it will be great. Okay, so I'll hand over the first page to Sis Christelle.
Okay, thank you, Michelle. And before talking about the periodic table, maybe I would like to talk about metallurgists. So thank you all Oluetu for the great introduction you've done with me. And I'm actually a metallurgist, and I'm sure people are wondering now, what is a metallurgist? So what does a metallurgist do? And in general, the metallurgists study the chemical property of metals and apply them to a process to extract the valuable metal from the rocks, from the ore. That is in general. And for example, a gold, they have copper and all those metals are extracted from the rock. And I work as a lab metallurgist, and what I really do in a lab. So we'll take an example of the what we are doing currently. I and Michelle. Michelle is a geologist, and I'm sure everyone know what is a geologist does. And so basically what she does is just studying the rocks and find out rocks are made with what and which metals. And then after that, she brings us the metal, and it's up to us as metallurgists to extract the metal we are looking for. In our case, it's gold. And in some other part of the world, they're dealing with copper, iron, silver, and all that. So as a lab metallurgist, my work is to guide the plant, because all this extraction process is through a giant process plant. And as a lab, my role is to guide them. And I do that by running test work. And my test work have a purpose first to confirm if really Michelle is giving us the metal she's claiming to give, and I'm here to ensure that she doesn't trick the plant, guys, and also to confirm if the metals can be treated in the actual plant with all this plant setup, and so that we can get good result, what we are looking for, like a good recoveries. And also what I do is, because all rocks contain, but they all behave differently. They have different chemical properties. So a process route for each metal to be treated in our actual plant, so that we achieve our goal, that is gold production. We achieve our goal by minimizing the cost of process and all that. And that is all what I do in summary. And today we're here to discuss about the periodic table. And so the periodic table, what is it? It is defined as tabular arrangement of chemical elements. That all we'll find in all books you read. You'll hear it from school. But me, I like to present the periodic table as the magic table. That it's the magic table that contains almost all the chemical knowledge one can have. So all the chemical knowledge we are trying to understand and to know, summarized in this one table. That's why it's cool. And I hope everyone will find it cool as I do. Not like I was talking to my niece previously, and she was like, no, she doesn't like chemistry. I was shocked, because after this, I hope that we won't have people that don't liking chemistry and the periodic table. And it contains all 118 elements that are grouped based on the physical and chemical properties. And based on that, they are grouped in 3 families that are the metals, the non-metal, and metalloids. So by characteristic, the metal are the good conductor of electricity, So the ductile, the malleable, and the contrary of the non-metal that are all the opposites. They are very poor conductors of electricity. And on the third family, we have the metalloid that are the mixture of the two. So they have the mixture properties of the metal and non-metals. And here the elements are differ from each other based on the electron configuration. That is the number of shell where the electron and proton sit. And then each and then all the electron configuration and valence electron, the chemical property that are grouped together and form the group in this periodic table. And next slide.
Sorry, I might be having a little technology hiccup. If you just give me one moment, I'm just going to stop sharing and share again.
Okay.
I can't press next. One moment.
No problem. Christelle, there's a question from La viewer asking, how do you know the contents of the rock? Maybe.
Sorry?
There's a question on the chat about how do you know the contents of the rock? So when Michelle put it to you, how do you figure out what's there?
Yes, Michelle.
Okay, let me answer that one. So for us to know the contents of the rock, the definition of a rock in itself is a constituent of minerals. So for you to know how much gold there is, for you to know how much silica there is, you have different ways of analyzing the rock. So you've got different ways where they analyze it by X-ray or analyzing it by different methods. And that can give you the chemical breakdown of what's in a rock. So in a similar way, that Christelle will dice it up and have a list of what minerals there are, is a similar way that we test out how much there is. But it comes in different quantities and it comes from different areas. So from the data that I have, that I would have drilled well in advance and got a picture of what this specific material is, I would be sending to the plant, and the accountability comes when Christelle and her team also analyze it, see what comes out of it, and then that's the power we reconcile all. Is the material that we're giving to them exactly that, or it's missing this, or it's mixed with other material, gang minerals, waste minerals that aren't really conducive for the plant. So all in all, part of this periodic table, part of understanding the periodic table is bringing back the knowledge that you have of the rock and everything else that we live with.
All right, thank you so much. All right, back to you, Christelle.
Maybe to add on that, on how we know the content of the rock, there is a study we call ore characterization that we do. It's basically what Michelle was talking. That study gives us all the chemical elements contained in the given rock. So we can have iron in the rock. We can have silica, we can have all that. And we focus on one metal that is now the economic that come in. So we focus in one metal. In our case, it's gold due to the quantity and the amount of gold over the other elements in that, so that we put all our efforts in to produce the gold and leave all that and leave all the rest.
Yeah. Okay, so I've managed to get on the second slide. So I think we can jump in from there.
Yeah. Yes. And okay, so the periodic table, what is it? I'm sure they will ask you in class what is the periodic table, but for today, there's some element I will want to keep in mind, and we leave this session knowing what to know about the periodic table, and instead of making look boring. So, and why is it called a periodic table? And why periodic? Why logical or any other characteristic? And to answer that, it's called periodic table only because the elements are arranged in rows and cycles that make a period. And so that's why the table itself is called periodic table. And they're arranged in a particular way that from left to right based on the atomic number, and the order is increasing. So the elements are arranged from the lowest atomic number to the highest. And itself, it contains 118 elements that are grouped in 18 groups. And each group, so all elements with the similar properties, chemical and physical property, are put together and form a group. So the group are just the vertical column of the periodic table. And it's easy when you see, when you know an element and you know its chemical properties, you can apply the same properties to all the rest elements in the column. So each group has different properties. And the other point is to know that each element is unique. Each element is unique. It has its own name, its abbreviation. We may ask ourselves, so who named the element? So since each one has its own name, who named the element? And back then, I think the rule was simple. It was just you discover an element, you name it. So all elements, some elements were named after places where they were discovered. So after people who discovered them, and so it's like anyone discovering an element has the charge to name it. And the elements are unique, differ from one another based on the atomic number and a number of electron and proton inside. And another point to keep in mind about the periodic table is that it has the 25 letters of alphabet except the letter G. Maybe everyone will go back and confirm this one. I did it. That's why I'm talking about it. It has X, it has Z, except the letter G. There is no element containing the letter G in its name. And we find the most common element, the element that we find in pretty much everything in Earth, the carbon, oxygen, hydrogen, and helium. And that is the summary of what I want to keep in mind about the periodic table. And if we can go to the next slide.
Yeah. So the next slide has got the periodic table as we all know it. So Christelle did a really amazing job at just describing how it's grouped together, how the elements are laid out, really well thought out, because they all fit in a sequence that makes us understand the periodic table and make sense of it and apply it in everything, basically. So the rows that Christelle was talking about are vertical. So you can see the color coding as well really helps with that in terms of understanding what is what. It's also really well put out as well. We've give an example with hydrogen. It's the lightest mineral. It's also number 1. So we'll go with some more details later on where we unpack the different elements and how the chemical layout in itself, what it means, and how you can make sense of it. But for now, we could just bring your eyes in terms of what does this periodic table mean. So some of these elements, you'll find them quite familiar. So when you look at number 2, the top right, you've got helium, and you might have heard of helium, or probably not. If not, you will hear about it a little bit more. And part of Christelle was saying that you got carbon, number 6, part of the most common minerals found, common elements found on Earth. You've got oxygen, number 8. You think I'll give you some examples. What is water made of? It's made of hydrogen, which is number 1, and number 8, oxygen, H2O. So you'll start to familiarize yourself with that. You got next to it, you got fluorine, and that's what toothpaste is made of. So things will start to make sense and bring you back to the reality of it. So in summary, what are we looking at when we look at this table, which can be quite daunting, but when you break it down, it's actually not too bad. So let's pick from 19. So we're going to go from the left-hand side and go all the way to the right-hand side. So we got from 19 going all the way to 36. Krypton. I think the only time you hear Krypton is in the movie Superman, isn't it? Yeah, so kryptonite. Isn't it? It's made its way into superhero movies. Not sure how, but it's really cool because it's a specific element that you find in some places, and high concentrations or low, but it was strong enough to make Superman weak. But in all, we're looking at now metals. So we've got calcium as number 20. And then we start to have chromium, 24, which these are mined in South Africa. You've got iron, mined in South Africa as well. You have nickel, mined in some places. You've got copper. We've all heard of copper wires used for electricity. And sometimes we have Amazama stealing a lot of this because it's a really useful metal. And then if we'll jump a little bit more and we'll go into these a bit more detail, you've got the other ones that are not too common to the common eye, but are used in so many things. The purple table right at the bottom, you got from 57 to 71. So these are called rare earth elements. And I think at this stage, it will be quite hard for you guys to understand what they are, but they're also very important. You find them in electronics. They're really good superconductors, and you get to dice them a little bit more in detail. You got the bottom ones from number 98, 89, all the way to 103. And these are your radioactive elements. So the way that the table is all put out is in really good order and in a way to be used in day to day. And we'll dice you and give you some more examples in a bit. So Christelle, would you like to add to the periodic table as it stands for now?
Yes, you have talked too much about it. And what I can just add, it's like, assume we all watch the movie, what is this, Wakanda?
Yes.
Assume we all watch, and we're talking about one element, vibranium. And all I wanted to ask that is a fictional element. It is. So it's a fiction. So the element they created only for that movie, it's not in our table. And so for now, we don't know where to find it. So it's only in our movie. I hope that that no one went and looked for the vibranium. It doesn't exist on the periodic table. So maybe they will discover it. Maybe someday.
Maybe someday, and it'll be us to find it, right?
Maybe someday, and it will be added on our actual table.
It's a really good point, actually, because if you look at Africa, we've got all these natural resources and we've got so much that we have in us that the world wants to have a pick of it, and so often does, right? So it's a really good thing. So getting to know your periodic table, you can go and discover more minerals and potentially make Africa high again. That's a good point. I like it.
Yeah.
Yes.
Maybe it will start with, it will have the letter J in it. And we'll discover it.
That's true. That's true. You've got a good one there. We're taking you along, Olu, to discover this new mineral. Nice. So we'll come back again into the periodic table as we laid out like this, and maybe we could jump to the next slide, and we'll be dicing it again.
Okay.
Cool. So this slide basically is just talking about why is this table so important. So we've made some examples looking at the table in terms of what the elements are, what do they mean. So I'll just give you some little examples just for us to give it some perspective. We've got water that comes out of a tap. But before it's drinkable, it's obviously cleaned, it's filtered, and then we add some more minerals or elements into it in order to purify it and make it drinkable, as opposed to just scooping water from the dam. So we've got things like iodine and chlorine. Iodine is over here. Don't know if you can see my mouse. And we've got chlorine also over here, and falls in part of the halogen gases. And then we've got the carbon in your pencils, which is graphite, and we'll come and talk about it again. We've got aluminum, which is what the cans are made of. So we're full of anything that we touch that is tangible, and even things that are not tangible that you can't actually see what's in the air is full of elements made of the periodic table, made from the periodic table. So other examples are technology, the phone that you have in your hand, the computer screens that we're using to have this meeting. So you've got the rare earth elements that I mentioned right there at the bottom. And you've got helium. Oh, sorry, you've got helium back there again, used in a lot of medical applications. Then we've also got the electricity that we use. You've got coal, you got uranium, you got hydrogen. So your uraniums are all the way down here. You've got your hydrogens here, and then you've got coal made out of carbon and hydrogen. So everything that we basically use, you can always pin it back to the table. But just to play a little game, and I need you guys to get involved here. How many elements do you think are used from the periodic table to make your smartphone? Now, bear in mind, this is a very big table. All in all, there are 118 elements. How many of these do you think are used to make the smartphone that you're using today?
Okay, so we have Lusang Bongo.
Lusanga, you can turn your mic on.
Hello, everyone.
Hello.
If I could guess, as I'm looking at my screen right now, lots of pixels, and I'm sure there's a lot of metals and other things inside of the phone. I'd say 50 or roughly 45.
That's a good guess, but I think you go more than that.
60?
Close enough. And let's give someone else a go as well. I like it. Between 50 and 60. You're getting close. You're getting warm. Let's hear some more guesses.
Somebody else had their hand up. Kungayi just wrote on the chat that she thinks it's 70 elements.
Also getting close. Also getting close. But we actually need more of those.
Silube.
Fantastic. He's spot on. 75.
Ah.
Yeah. So there's quite a lot that goes into your smartphone. And I'll give you a little image in a minute, but keep in mind you've got these rare earth elements and the lanthanides. So number 57 all the way to 71. So a bunch of these ones that we barely even hear of, they're very much involved because they're the ones that they're the superconductors. They can carry charge in a very small surface area in quite a powerful way compared to your traditional copper and sometimes gold. And then, like you had said, if you just look at your phone itself, you're looking at your screen and everything else that falls under there, which is made up of quite a lot. So let me go back to this screen over here. So what does the phone have? It's got a battery. Most batteries are made of lithium these days. Sometimes they substitute the lithium for cobalt, so you can have some of those. Then you've got silicon, which makes up part of the complex part of the phone, the motherboard. And then you've got gold, of which Christelle and I mine and provide to the world. You've got tin. So just to go back to the gold are used as superconductors as well. So it also carries the charge. You've got tin, and tin is particularly used in the smoldering. So the joining parts between all these metallic bits that need to carry the information for whatever functions that your phone is carrying. You got tin. And we'll come back and just keep in mind of these names. And every time we come back to the periodic table, we'll be pinpointing where you find these elements. All right? And then you've got your screen. And your screen's got a whole composition of elements. Part of it is glass, but also a polymer of glass and plastic. So we're mixing aluminum, silicon, potassium, oxygen. And these are these rare earth elements that are highly sought out. You can get them anywhere in the world, but not in high concentrations. So they're very hard to find, very hard to explore, and are basically the next thing to find because that's where technology travels. So,
sorry, Etienne, if you could please make sure that your microphones are on mute. We can see some background, hear some background noise. Sorry to interrupt, Michelle. You can go ahead.
No problem at all. Okay, so just keeping an eye on all of these, and looking at the periodic table again, we've got these rare elements all falling down here. And then you've got your ions. I didn't show all the minerals themselves, but you've got the gold, you've got your gold falling in here. You had aluminium falling in here. So there's quite a bunch of stuff that all join in. I think we also had tin. Can someone spot tin for me? And it's not written as tin, it's written as SN.
Lovey will say this is number 50.
50.
Yes.
Yeah, well done. Well done. So you could just see just how wild, how open and wide it is, and just has so much to give and so much to learn from. Okay, now the next example that we're gonna dive into is what a car's made of. And we discovered that cell phones or smartphones are made out of 75 elements in the periodic table. Believe it or not, you need less for cars. So typically, depending on the car that you have, you can go from up to 30 up to 40 elements in the periodic table. And it's amazing, right? How a little thing such as our cell phones have so much complexity and so much variation compared to cars. But anyway, coming into cars, what are we looking at? So, can you see properly?
Yes, we can see the slide.
Fantastic. Okay, so we've got iron, we've got aluminum, we've got carbon. I won't read all of them in detail because we'll take the whole day. But all of these different elements have the different properties and different uses. So unpacking the car itself, you've got the battery, of which we mentioned also in the phone that we use lithium. So lithium is quite a key component in batteries, number 9. We also use cobalt, which is also a key component in the batteries in itself, but it's also used in some of the alloys that we need from the engines, right? We got platinum. We have quite a few mines in Rustenburg and in those areas where we're mining for platinum. What do we use platinum for? It's quite good actually, because it's that key component in your catalytic converters. So if you didn't have the platinum in it, you'd be spewing out dark fumes that are coming out the engine. So really interesting, really important part of our daily lives, and just dicing it just makes it more interesting. The other example I picked was iron. So we've got iron mines in Kuruman in the Northern Cape. And that's what makes up most of the car, with the car frame and part of the other alloys that we'll need. And an alloy is basically just a mixture of different metals. And then we've got something really interesting that is not normally known. And I think it's in the next slide. Okay. So I'll also share this slide just so you guys can pick it and work through it and just understand and take it with you with life. So as we're continuing, we have a list of about 31 in just a normal Toyota car. What do we have here? I've picked examples of sulfur. Now, sulfur, hard to imagine how sulfur, which is a non-metal item, can be involved in a car. And I picked some examples of where you can find sulfur as well. So this picture just on the right-hand side it's a place in Ethiopia called the Dalol volcano. And sulfur naturally it's a mineral that's made and comes out naturally from volcanic activity. So it can come in crystals and it can come in dust form. What do you actually use it for when it comes to this? So when you have tires are made out of rubber, and rubber is made out of these days anyway, it's no longer taken from trees and stuff like that. These days it's a constituent from the oil processing. So once you've made rubber in its form, you can burn it basically with sulfur, and that changes the structure of the rubber in order to have really strong tensile strength used for tires. And this is something that we don't normally come across. We just see the tire completely finished and done and used, right? And then you've got potassium, which you also saw from the picture with the phone. And this is in the glass. This is in making of glass and part of the engine coolants. So not only do you have the metals part of the periodic table, but you also have the non-metals, and they all play a very big part in making the items as we know. And then this picture of gold over there is the mine that Christelle and I work in. And gold is pretty much used, as I was saying, in high-end electrical connectors and conductors. And not only is it used for currency and many other things, but it's a very good conductor. So yes, dive into this example when I share it with you guys, and just pick out what is interesting to you and throw in some questions if you need.
There's a question on the explanation of vulcanization in that first bit when you explained the use of sulfur for tires. I think Gabiro wanted a little bit of a breakdown on what that means, vulcanization.
Vulcanization. It's basically heat. It's high pressure heat, and I'm guessing injection of sulfur in itself to change the chemical bonds of the rubber tires from being a loose sort of structure to these strong bonds, and that make the strength of tires and have that tensile strength. So the vulcanization is just a process of heat and injecting sulfur.
Okay, cool. There's a debate going on in the chat about what makes up a group 3 to 7. Are they all metals? Is it metals? On the periodic table, also another question on alloys.
Okay, maybe I can let Christelle jump into that one. What was the question again?
So there's a question around whether group 3 to 7, if those are
Yes.
metals.
Yeah, these are metals from 3,
Okay.
yeah, 3 to
Wrote
7. Okay, if we can go back to the first slide, Michelle, let's see where the metal sits. And so we have the group 3 to 7 here, which are metals. They are part of metal.
And then what are alloys?
Alloy isn't simply, I can just say alloy is it's a combination of 2 or more metals. That's the simplest answer I can give.
Exactly.
Okay. All right. Thank you, Christelle. Thank you, Michelle. You can continue. We'll bank some of the other questions for the Q&A session at the end.
Yeah.
For sure.
And I'm sorry, I'm trying to, so my camera is giving me issues here, so maybe I will continue without a camera.
As long as we can hear your voice and your brilliant mind, absolutely fine.
Thank you.
Brilliant. So those are the components making up a car. And I'll then give you guys a break from my voice and let Christelle jump into the chemical element in itself and what does it mean?
Oh, yes. And talking about all the components we get in our daily lives. So we have to know that everything that we can touch, so some other thing that we cannot touch, are made of a chemical element. So I will ask, so what can we do? What is life without a chemistry, without a chemical element? The answer is easily nothing, because there is chemistry, there is chemical element in pretty much everything. So all the matters that are found on the surface of the universe, there is a chemistry in it, there is a chemical in it. So a chemical element itself is just substance that's linked to others and form some bigger substances we call chemical compounds, and we go above, we call a chemical molecule. So that is a whole lecture that we can have maybe some other time. And we use the chemical elements to form like bigger substances, bigger matters. For example, the easy example is water, the water we all drink. That is formed by 2 chemical elements, hydrogen and oxygen. And a chemical element itself, it's made of some parts. It's made of the atom. And the atom are made of the proton and the electrons. So all that make a chemical element. And yeah, I hope I've explained what is a chemical element. So Michelle can take us through an example of water.
Yeah, that's it. So as Christelle was saying, once you dice the actual element in itself, right, it has an atomic structure. And within this atomic structure, you have the electrons, which is, given the example of the hydrogen, you've got this electron that moves within the orbital. And this is really important because this is how these elements interact with each other. So if you've got oxygen, taking that as an example, oxygen has 8 electrons altogether, and then it's got the 2, well, it's got 6 basically, and it will be most stable at 8. And the 2 electrons that are on the outside carry a -2 charge. And there's a nice example that we're going to show you in a video of how these interact together and what do they mean when you've got a negative charge on one element and a positive charge on the other element and how they interact together. But just to show you a little diagram of how water interacts with each other, you've got oxygen's 2 electrons free within the outer shell, and that bonds with the hydrogen plus 1 electron that is also free and creates a stable shape and a stable molecule, and that's how water is formed. So If you bear with us one moment, I'm going to jump into a video, and that will give you exactly what I mean. And it will be just helpful to break it down and see how they all interact and make sense of it. And let me know if you can hear.
Covalent bonding.
Perfect, can hear you.
Luckily for us,
Wow.
atoms don't just sit around. They stick to other atoms and create amazing things, like the salt and vinegar on your chips. So, how do they do it? Well, one of the main ways is through covalent bonding. It occurs in most non-metal elements, and it's how atoms bond to form molecules. And these can be elements or compounds, so made up of two or more different elements. So what brings these atoms together? Electrons. Most atoms have outer shells of electrons that aren't completely filled up. They've still got room for some more. If they share electrons, they can fill up their outer shell and form molecules. And when two atoms get all cozy with each other and share a pair of electrons between them, that's a covalent bond. To draw covalent bonds, we use dot and cross diagrams. For instance, carbon dioxide consists of one carbon atom bonded to two oxygen atoms. Now, carbon is in group 4 of the periodic table, so it has 4 electrons in its outer shell. And for that outer shell to be completed, it needs 4 more. Oxygen is in group 6, so, you've guessed it, it has 6 electrons in its outer shell. So when forming carbon dioxide, each oxygen atom shares 2 electrons, forming a double covalent bond with a carbon atom. When that happens, the outer shell of the carbon atom is completed. 4 of its own electrons and 2 from each of the oxygen atoms. So do note that both oxygen atoms still have 4 non-bonding electrons that are just left over. Now, there's a difference between simple covalent structures and something called giant covalent structures. Methane, the gas that's used in your Bunsen burners, exists as simple covalent molecules. So that means the atoms in each individual methane molecule are held together by covalent bonds. But there's not much holding one molecule to another, only weak intermolecular forces, and it doesn't take much energy to overcome them. On the other hand, giant covalent structures are made up of a huge number of atoms, all joined by covalent bonds in continuous 3D networks. For example, let's have a look at diamond. That's made of carbon atoms, and each carbon atom is bonded to 4 other carbon atoms to form a continuous regular lattice. Covalent bonds are strong, and there are loads of them in diamond, making it the hardest natural substance in the world and giving it a ridiculously high melting point. Graphite is another giant covalent substance, and though it's made from the same stuff as diamond, it is nothing but carbon atoms. It's really quite different. It's all soft and slippery. Why? Well, in graphite, each atom is bonded to 3, not 4 other carbon atoms. And they end up forming layers with only weak intermolecular forces between them, making it all slippery and crumbly. The carbon atoms in graphite don't share all their outer electrons, so they have non-bonding outer electrons. These electrons are free to move around the lattice, which means graphite can do something rather useful that diamond can't. It can conduct electricity. So, there can be a fair bit of difference in the way covalent structures are formed, but they all contain those strong covalent bonds, which of course are just atoms sharing electrons. Well, sharing is caring.
Wonderful. So that was a really good example on just to break down the different types of how the different elements interact with each other and create bonds. So like the diamond and the graphite example, and graphite, just to put perspective, is what's in your pencil. So it's slippery, it's dark, it's black, and yes, in some cases, it is used for conducting of electricity, and in some places it's used for pens. But how do you have the exact same element as diamond and it can behave in so many different ways? And as Lady Lovely explained in the video, it is a case of the different types of bonds that you have between these elements. So the three different types, so your covalent bonds, are your ionic bonds, and are your metallic bonds. And I'm just gonna throw another video of the ionic bonding, and after that we'll just dive into some different examples, and we can pick around what's at home.
Ionic bonding.
And that we can give examples of.
Ionic bonding is all about opposites attracting. Not that kind of opposites attracting. We're talking about charged particles, known as ions. Ions are formed when atoms lose or gain electrons, and that makes them either positively or negatively charged. Oppositely charged ions are attracted to each other by really strong electrostatic forces, forming what are known as ionic bonds. A good example of a substance containing ionic bonds is sodium chloride, or as we call it, table salt. It's a compound of a metal and a non-metal, and it's made from positive sodium ions and negative chloride ions. Ions form when electrons transfer from metal atoms to non-metal atoms. The atoms of sodium and other metals have incomplete outer shells. When they react with a non-metal, they lose all their outer electrons. So the shell below becomes the new outer shell, and it's complete. It has no space for any other electrons. An atom that loses an electron becomes a positively charged ion. So sodium atoms are written as Na, while sodium ions are written as Na+. But the electrons must go somewhere when they leave metal atoms, and they do. They're gained by non-metal atoms that have incomplete outer shells, making those shells complete. The extra electrons turn the atoms into negatively charged ions. So chlorine atoms are simply written as Cl, while chloride ions are Cl-. And look, now the ions have opposite charges. Opposites attract, and electrostatic forces pull them together. That's your ionic bond right there. Hello, table salt. So, ions can form amazing structures, not just table salt. In ionic compounds, the oppositely charged ions attract each other from all directions, forming solid structures known as giant ionic lattices. Ionic bonds are really strong. It takes a lot of energy to break them, meaning ionic compounds have high melting and boiling points and are solid at room temperature. Another property of these structures is that they don't conduct electricity when they're solid. Why is that? Well, an electric current is a flow of charged particles. Solid ionic compounds don't conduct because their charged particles, their ions, can't move about. They're locked in place in the lattice structure. If we want them to conduct electricity, we have to break the lattice up by melting or dissolving the ionic compound. So there you go, the strength of opposites attracting. Really?
Fantastic. So really enjoyed that video because it just gives some perspective and diagrams in terms of how these things interact and what they mean. And I did say I was going to give you some examples. I'm sure you've all seen jig bleach, and there's some examples from covalent bonds from there. You've got ammonia, which is used in quite a lot of cleaning material. You've got ethanol, which is the alcoholic substance used in hand sanitizers. You've got paper. Paper's made of cellulose, and the bonds between the carbon, the hydrogen, and the oxygen, that's what makes the covalent bond and what makes the structure of paper. And sugar is a good example as well. To the right, we've got the ionic bonds. We've got baking soda for you guys that do baking. We've got Epsom salts. And I did mention that you got fluoride in toothpaste. Plaster of Paris, which is the cement when you break your bones. That's made of calcium sulfate, and that's an interaction of ionic bonds. And then you've got Eno, when you have an upset tummy. drink a bit of Eno. It's an anti-acid. It will calm down the acidic stuff that comes up from your throat to your esophagus. And there you go. You've got examples of your day-to-day life all put together coming from this periodic table. And one we don't talk too much about is the metallic bonds. And the metallic bonds are between two metals, and quite often you would have the intermolecular forces joining the bonds within the same element. And I've got some nice examples. You've got aluminium foil that's used in the kitchen if you're baking or putting stuff in the oven. You've got the copper wires that take electricity from one place to the other. Those are examples of metallic bonds. And the spoons and forks that you have for cutlery, and those are made of different alloys, sometimes silver, iron, chromium, nickel, and quite a few other metals that differ because of price and what's practical. But yeah, in our day-to-day life, you've got the periodic table basically everywhere. All right. Before we jump into the next slide, Christelle, would you like to add anything else, or shall we continue to the last slide? I see we do have a few questions.
Maybe we can see what are the questions on this one before we continue, and then we can answer.
Sorry, I'm trying to see what questions refer specifically to the slide. There's a question on giant lattices. On what are those?
Okay. A giant lattice. Okay. A giant lattice are structures that are held together with ionic bonds. I think. Michelle, am I right?
Yes, no, 100%.
Yeah. So that is lattice, giant lattice. So they are the matters held together by ionic bonds.
Most times. And the lattice structure in itself, just for language purposes, is the different types of bonds as well. So even though we'll have the ionic bonds held up on one side of the structure, you'll also have the intermolecular forces in between. So we'll make an example soon after with ice. So even though we have the structure in itself of the different hydrogen and oxygen, and even with those, we also have the next layer of bonding, and those ones in between make up the lattice structure, which makes up a much stronger one. So combination of ionic bonds and the intermolecular forces as well.
All right. And then at the top there, you have a picture of Greek bleach. And Usango wants to confirm if ammonia is an acid. There's some feedback from the other FGLers that are saying it's a base. So some clarity on that.
It's a good question, actually. It's the definition of an acid and an alkaline is the pH, right? So what is the pH of ammonia? Someone can give it a Google, they can get a good answer from there. but in its Greek form, it will be quite, it won't have too low of a pH or too high of a pH because it's mixed with other substances, water, and all the other reagents to balance it in order for us to touch it with our hands. So ammonia in itself will be quite, is it a base? I think it's a base.
I think I can add like acid identified with the hydrogen ion, and ammonia itself doesn't have that hydrogen ion. So based on that, we can say ammonia is a base, it's not acid. But when it reacts with water, now we need to read more. When it reacts with water, it forms that hydrogen ion. And that maybe can form an acid then.
Okay, all right. I get that now, Christelle. I hope, Lusango, your answer was found there in that response. Love you is also giving some feedback that it's weak base with a pH level of just above 10, I think.
Oh, very nice. I'm enjoying the debate, actually, just tuning in. Very well done.
Another one on sulfur. Can sulfur change forms, liquid, solid, or gas naturally? And is it the only one?
Can sulfur change forms? Yes, it can. And it depends what's it bonding with. So that example I had of the Dalol volcano, when it dissolves with acids, and these are hydrothermal acids. So these are acids that come through from basically the magma, between the magma and the crust. As they come up, they dissolve some elements and minerals as they come up through the fault zones. And in that case, they will be in liquid form because they're dissolved in acidic fluids. But the deposition of them will depend if it's getting deposited in water or deposited in between rocks or through crust. So it will depend. And then turning it into gas is just a case of moving it from different phases, and you break those bonds by increasing the level of temperature that you expose it to. But in its natural form, it comes mostly in solid state, in a crushable, tangible, solid state.
Fantastic. All right. Thank you, Michelle. We can continue with the rest of the presentation and maybe go through the rest of the Q&A after.
Okay, fantastic. So we're down to our last slide now, and we want to bring the presentation back to the room so we can get everyone involved. So we want to do a group activity, and we're calling this the element scavenger hunt. And basically we'll put the periodic table back in, and I'd love someone to grab something that is nearby them. And then we'll try and dice together, what do you think are the elements that make up, for example, this glass? So I can start with my glass, and then I can ask you guys to jump in and tell me what makes glass. It's gonna be a tough one. Not everyone knows the answers, and that's what's great. Not even myself. So jump in.
Can I try?
Yes, have a go.
Okay, ma'am. I'm not sure if it's only this substance that makes up glass, but I think when I was around grade 5, my NS textbook said that glass was made from heated sand.
Love it.
Yes.
Love it.
Yes.
That's perfect. And that's going to fit into the question, how does sand make glass? Okay, brilliant. So it's made of heated sand, huh? Wonderful. What is sand? What are the elements that make up sand? And you're welcome to Google. It's not a tough question. You guys jump into Google, find out what are the elements that make up sand. Christelle, you're welcome to join in as well. Give me a guess.
Yes. Yes. Honestly, I'm also Googling. But we find silica in sand.
Yes, we do.
We find oxygen.
Correct.
Yeah, those are my 2 elements. So I'm leaving the rest to the team.
Well, you've got it spot on. It's silicon dioxide. Right?
Oh.
Yes. Sand, or the part that is extracted to make up glass, is silicon dioxide from the sand. And where's silicon? We got silicon in number 14, and then we got oxygen here. So Silicon would be Si plus 4. Someone can correct me. It's in group 4. So it's got 4 electrons on the outside. Oxygen is in group 6. So it's got a 2 minus. So silicon dioxide is SiO2. And right there, we've got ourselves glass. And obviously there had to be a lot more into it in terms of purifying, in terms of clearing the glass color, in terms of all the other interactions that would have come through to make this glass as we are. But as it is, just pure glass is silicon dioxide. And I don't know if you guys watch Game of Thrones. If you go to Dragonstone, they have obsidian. And obsidian is the one that killed the White Walkers, those dead creatures that crossed the wall. And dragon glass is basically just new material that came from a volcano and cooled really fast. And that's actually glass. That is a volcanic stone in its purest form. And it's literally heated up sand to make natural obsidian, which is glass in its natural form. So yeah, first scavenger hunt. Well done. Well done. So next one. Oluetu, what do you have on your table that we can all jump in for a scavenger hunt?
Apart from glass.
Apart from glass.
I have got a set of car keys.
Ooh, that's going to be very interesting.
What is that? I didn't see.
It's car keys.
Oh, okay. Oh, yes. Wow.
So the car keys has got
so
metal,
many elements in it.
metal bits, it's got plastic bits.
Mm-hmm.
What else does it have? So the plastic is colored black.
So plastic is carbon. Surely it's got carbon in it. That metal can be is it steel or iron?
There's somebody that has a hand up.
Someone's got a hand up. Let's see what they say.
We have Lusango.
Yes, Lusango.
The metal bit is most likely an alloy of, so it doesn't break. It has iron. If I could guess, it's an alloy of iron, a bit of nickel, and maybe sodium. That's a hard guess. But then on the plastic bit,
Yep.
It's a non-metal. And on the inside, since it has electricity, it most likely has silicon in it as well.
Mm-hmm.
And on the bit is a non-metal, so it's a little bit of a stretch on that one. So I'm gonna leave it to someone else.
Okay, very good though. You're on a good point. I love it. I love it.
Did I see Sibabadu's hand up or just a comment?
It was Laviwa. But the hand
Laviwa.
has gone down. Yeah, the hand has gone down.
While we're also tuning into more answers, remember in the car key, we've got some electronics because you press a button and it locks, right? So you've got a motherboard under there. And remember when we're in the presentation, we showed that there's a lot more elements going on inside that key. So give me a guess. Keep discovering, keep looking at the periodic table. What else was in that motherboard besides the metal, besides the plastic?
Olotando had the hand up.
No. I'm not sure, but I feel like the reason why ice floats on water is because I don't remember if it's because the ice becomes less dense or more dense.
Wrong answer. We're not going to that question yet, Olo. We're asking about the electronics inside the car keys. What are some of the elements in the periodic table that would make this car be able for me to be able to open my car and lock it. So there were examples of elements that are in perhaps a smartphone, also the cars that the elements that make up the car. So what are the electronic parts that are likely to be in this motherboard that allow for me to open the car just pressing on a key? Did someone already mention silicon? I'm trying to guess. I think silicone and lithium. Am I making it up?
Can I try?
Yes, go ahead.
So the other elements that were part of the motherboard, there was tin, there was gold, because Michelle said it's part of the conducting materials, and then the silicon, and yeah, there was also lithium, but lithium is for the battery.
100%. 100%. Love it. Love it. That's exactly it. That is really good. And obviously when your car battery, so when your remote battery is out, then you'll have to change it. And normally you have those really small sized batteries that you just interchange in your car keys and get it replaced. And yeah, most of the time they will be made of lithium. So very well done. Love that answer.
Nice.
Sure.
Is there anything around you that you see that we can look at what the components are? All right, I'm sitting on a chair that has a lever that can go up and down.
Mm.
It's got, I think it's like plastic arms.
Mm-hmm.
I don't know what the mechanic is that allows it to be able to move up and down. What is that?
We've got some structural levers. Yep, I do too. Yep. Yep, excellent. So they've got the type of metal.
Yes.
That feels light. That feels light and not very heavy. If I can go back to the car example, we've got different types of metals that are really good that need to be lightweight. So if you mix, say, take number 12, magnesium. Magnesium is used in alloys, in this case in aluminum alloys, and it has the components to make things lightweight. So where was magnesium again on the periodic table? 12. Yep.
We have a hand from Isivile.
Okay.
Yes, Isivile, go ahead. Isivile, are you there? All right. Sis Michelle, maybe you can continue explaining and maybe she'll pop back in.
Okay, maybe she'll pop up. Sure. So you got magnesium.
Okay.
Yeah.
No, go ahead.
Okay. Good evening, everyone. So I just wanted to state some elements on the chair. So on the chair, so there are some parts that are plastic. So I just found out that parts in the plastic chair are carbon, hydrogen, oxygen, nitrogen, chlorine, and sulfur.
Yes. Yes. Fantastic. I love it. I love it. Yeah, you can keep going. You can keep going. And then you got metal bits as well, don't you?
Oh, yes, we have them, but I just only researched on the part of the plastic.
No, it's good. It is good. It is good. You could also check the different types of metals, right? But we also have like this cloth or some sort of cotton, right? So yeah, maybe you can give us a guess. What is cotton made of? What are these elements that make up clothing? Because clothing is also made of elements. So what is it? What are the different, so maybe someone else can also look this up. What are the different pigments that make up the dye, the coloring of this purple shirt or Sisoloeto's black top? What are the pigments that make her jumper black? So there is so much that we can all learn from this by just dicing and unpacking just one item and seeing how many things go into making it.
Someone also said they have a heater in front of them, classically, because we're in the middle of winter here as you're enjoying summer in the UK. What are the elements that would make up a heater? I guess it depends on the type of heater. Hey? Ungwayo, what type of heater do you have in front of you?
I have a metal heater in front of me. Sorry, good evening to everyone. I have a metal heater in front of me. Thank you.
Okay. And what do you think are the elements that make up that heater?
An electric heater or gas heater? I'm guessing electric.
Electric one.
Okay. So just give us a guess. Give us a guess. What type of metal do you think it is? Unpack the electricity comes together, heat up the element and gives off the heat. What do you think those joining things are? And give it a Google. Let's see what you guys come up with.
Ma'am, I feel like there's sulfur in the pot where the heater turns on, like the glass-like or metal-like, where the bars turn red or something. I feel like there's some type of filament that's like sulfur.
Okay. Why do you think that? Tell me about your research.
Oh, Mom, I didn't make research. I'm also sitting in front of a heater.
Pile is suggesting that there's copper. There's a copper element there because it's a conduit.
Yep, and it's a good conductor. Very good. Love it. Love it. What else is there? There's lots of stuff that make up that.
Maybe carbon.
Maybe what? Sorry?
Carbon, because we did say it's also a good conductor of electricity. Maybe also thermal use.
I don't think I heard you properly. Which one?
Carbon as a good conductor of electricity.
Graphite can be a conductor of electricity, but in the form of a heater, it would only be the metallic structures that would conduct. So mostly copper.
Okay.
And then yeah, but it's a really good thing you mentioned that, because you still have a lot of material that are made of carbon, right? So, but in the case of the heater, less likely will be graphite, more likely will be the metallic copper linings that join in the two things that get the charge going from the electric point into the filaments. So the filaments made of I don't know myself. I'm also asking. I'm curious. very, very curious. And this is what's wonderful by just like unpacking. We all get to
And
learn.
I can guess you're seeing the complexity of the heater. I think we don't have like a single element in it. I think we will likely have alloys in the heater. So it will be a combination of 2 or 3 metals.
Sure.
What's nicochrome? Nicochrome. It keeps coming up in the chat. Is it nichrome?
Nichrome, is it chromium and nickel? Probably. Okay, Michelle, can you get us back to the periodic table?
Periodic table, yep. Here we go.
So, is it nicrocom? Oh, I don't know.
That's how it's written in the chat.
Maybe it's a alloy of nickel and chromium.
I think it's an alloy as well.
Yes.
Oh, very well done. Nice. Copper,
Yes,
nickel,
we have
aluminum,
nickel at 28.
and iron. Chromium oxide, nichrochrome. Very well done. Nice. But yes,
Yeah.
alloy. Definitely an alloy.
Yeah.
Which is a combination of both. I love it. Okay. Which other examples can we dive into? Actually, we haven't even finished the heater. The heater will then have a cord, right? And inside the cord will be more copper, and then will be also surrounded by plastic. Wouldn't it? So you want to dice up plastic, you've got your carbon, your hydrogens, because it's a polymer of a hydrocarbon. So, and then also mixture of all the other elements as well, different pigments to have color and stuff like that. So very well done. Very well done. Okay. Do we want to jump into another example as well? How much time do we have?
We'll have a bit of time, about 20 more minutes, so we can jump into some more items. If FGL is anything in front of you, maybe
Can I suggest?
Yes, sure.
So Michelle asked what our clothes are made of. And actually our clothes are made up of the same thing that makes paper, which is a cellulose molecule. It's C6H10O5. It was in one of the slides.
Was indeed. Yeah.
Wow.
Yeah.
Very
So
nice.
it makes our clothes and paper and other objects.
Love it. Thank you so much for that.
This is brilliant.
That's absolutely brilliant. So then, with that said, just keep your mic on. With that said, why do we have paper with that structure and we have clothing with this type of structure, even though it's made of the same thing? Why do you think we have those differences in texture and feel, even though it's the same thing?
Ma'am, I think it's because of what you said earlier, the ways or the types of bonds that exist between the atoms, the elements.
Yes, 100%.
Wow.
Exactly that. You guys are way smarter than me. It took me forever to understand.
Yes, we are learning from this.
Literally. This is brilliant. I love it. Excellent. Excellent. It is exactly that. It is spot on. So when you do go on and continue this world, because we last see the periodic table in this detail at high school, yet we still use it today. We still use it today in our work. So if the material or the gold or the rocks that I gave to Christelle and the plant, they still dice it and use different reagents and acids and bases and other reagents that break down the rock in order to get the gold out. And maybe Christelle, you could also dive into the details of it, how carbon attaches to gold, and that's how you leach the product out of it in big tanks, and how it floats out and get to the end. And it's literally an understanding of how these elements interact with each other, and at the end we live to, grow industries and have conductors and gold and whatever we have.
Yes, everything we do is based on this table. As I said, we have the rock. We are looking for the gold in the rock, but the rock come in with the different properties. The gold is combined to many different elements. So we can have some gold oxidized with the more oxide that we call the oxide ore. That is a way different from the rest. The rest the gold can be combined with sulfur. So it can be a combination of sulfur and iron that make a pyrite. So they all contain the gold, and we cannot treat them the same way, just because of the different element in that. So with the oxide, the gold with the oxide. Michelle, can you remind me oxide mineral?
Carbonate is an oxide mineral. In terms of gold?
Yeah. Is it galena? Oh no, shit.
Galena is more of a lead oxide, yes.
Yes.
We can make some more examples for copper as well. You've got malachite is an oxide mineral. I think that one's easy to view. I can just show you some pictures. You know, the green, really wonderful green malachite, that's an oxide. And then a one that's very hard to recognize, boronite. But someone's struggling with
network and audio. All right, better. Okay.
I think this one's easy for some people to see. So you'd have these bright carbonate, and then you have your boronite. So things that come like this with sulfur. What can I say? It's bringing you structures rather than. So you have a lot of pyrite, as I'm saying, that comes into sulfides.
Yeah, anyway, I was saying that the difference between the element that combine with gold that we get in the plant, and we have to treat them separately. So the oxide part, the oxide ore will be treated different from the sulfide. And so the oxide will be easy. We are targeting the gold, and we will use a chemical that's a combination of carbon and it's CN, and that's what that's a compound, and that's what attack gold in the ore and leach it and make it in the solution in a liquid form. And then after getting the gold in a liquid form, we put in carbon. Carbon has a property on its ore. So we can call it the ore on its surface. So it has a pore on its surface, that the carbon. And that's where gold goes and get absorbed onto the carbon. And then we carry that carbon and use heat to get back the gold. And then after that, we use the electrowinning, and we can get the final product.
And the electrowinning is basically those ionic charges. Remember when one was positive and one was negative? And remember when in the video we were talking about how you don't have charge in solid structures. So in electrowinning, the material moves in a liquid form, and you've got positively charged cations, right, moving to anions. And this is how you have the elements moving to one end to be absorbed in the other and liberating the gold right at the end. So it all comes into play in the real world. And there's a perfect example of the world that we live in that still has very practical applications with the periodic table.
All right. Olotando, we cut him off earlier. He was super keen to answer the question about ice floating on water. Olo, are you still there?
Uh, yeah, I'm here.
Go ahead. What is your theory? Why does ice float on water?
I feel like ice floats on water because I don't remember if it was because the density of water and ice is different. Because it's because ice is either less dense or more dense than water. That's making it float.
That's true.
That's
It's less
exactly.
dense. Yes, very well done. It's less dense than water. But why is it less dense than water? Let's go back to that video where we're talking about the structures, the giant lattices, intermolecular forces. Why do you think it's less dense than water? It's made of the same thing.
Okay. I think it's because since it's frozen, I feel like the atoms they change in a way, making the density different.
Okay, it's a good point. It's a good point, but it all comes back to the type of bonds. It all comes back to the type of bonds, right? And maybe someone else can also jump in, give it a Google, give it a read. But basically, when you freeze ice, right, the bonds themselves loosen up actually. They loosen up. So they're much more closer together in water. And that's why they're a little more dense. But they are locked in ice. So you still have your structures of your H2O, your covalent bonds in between, and you have your lattice structure where you have your intermolecular forces. And those themselves are locked and have enough space, if I could say, and that makes it less dense because they're locked in a certain structure. Whereas water in its own liquid form, water is actually really interesting because gas behaves completely different, like steam. And water in itself will have a lot more, the forces are much more tighter in its form, and that's why you'll have one that's more dense and then less dense. But the key difference between those two are the type of bonds and the type of intermolecular forces. That's literally it. It all comes down to it.
Maybe can simply explain that. So when you freeze water, the crystal it forms the crystal particles that bond to each other and form and occupy a higher volume. That's
Yes.
simply like that. So what is density? Density is mass over volume.
Yes.
So in glass we have a higher volume, the same mass, and in water the volume is less. So that is making a glass to float on water. Can simply explain it like that.
100%. 100%. So the ice structure is strengthening the bonds, but it occupies a lot of volume and has lighter because it's less dense.
Yeah. Yes.
Amazing. Nice. What about, let's make it a bit more interesting then. Salt. If you put salt in water.
Yeah.
And you could see this. You could see this in you can see this if a river comes into contact with the ocean. One is more dense than the other. And you can see when some of the two oceans come together, like the Atlantic and the Indian Ocean, when they come together, there's a massive difference in terms of density, color. One floats under the other. So who's taking that answer? If you put salt in water, does it make the salty water more dense than the fresh water, or the other way around?
Trying to see who has a hand up.
Yeah. And take your time. Give it a Google. Have us like check pictures out. check pictures out because it's really interesting. And the next time you're in Cape Agulhas and you see the two different oceans joining together, you'll be like, huh, I know why. They might not believe you, but you know why.
Lovey was asking that if you could please ask the question again. So it's salt and water, and you're asking why the other would float underneath as the two oceans come together.
So I was asking if you have salt water and fresh water, which one is going to float on top of the other? So the one that floats is the one with less density. So is the salt water less dense or is the fresh water less dense? Let's we've got a few hands up, and Mama Christelle, you can take these up.
Lindisipho. Hello everyone.
Hi.
I think that the salt water is more dense because of the salt particles that dissolved in the water. So the fresh water will definitely float on top of the salt water. So yeah.
So salt water is more dense.
Yes, it is.
Okay, excellent. Mama Christelle, would you like to add to that?
Salt water and fresh water.
But yes, it's correct. 100% correct. And then why? Why is it more dense? You mentioned that you've got more. Could you continue the sentence?
So what are you saying? Why is it more dense?
Yes.
No, the young man. Our young man had a really good answer, and wanted him to, yes. I just wanted him to continue educating us in terms of it's got more elements. You said in it, it's got more. I just wanted to capture your full sentence.
Oh yeah. I said that the salt water has dissolved salt particles in it, so it has more mass and therefore it's more dense.
That's a really good answer. I like that a lot. And then also what we didn't touch on, still on the salt water, still on water, what we didn't touch on, and it's quite a tough one, it depends on how far you are in school, is now the boiling temperatures and the melting temperatures. So fresh water and salt water, one of them is going to boil at a lower temperature than the other. So these are the type of things now that get really interesting and also will have an impact in work or life or just understanding how things work. So in countries where it snows, they put salt in trucks and then they spray the salt and then that melts the ice and then you can clean up the ice so that you can drive on the main roads. And that's because salt reduces the boiling point and makes it melt quicker. So those are pretty cool. And you can see this pattern in the periodic table in itself. So once you get to know it more, you'll also start to put in melting points, boiling temperatures, etc., etc. So something just to keep in your mind and to look forward to the next time you're jumping into the periodic table. Cool.
All right, we have about 4 minutes left. I want to try and get to some of the questions we didn't get to. Noble gases, a question on which group they fall into, and also how they react with other elements. That came through from Umbalente.
And sorry, can you repeat the question?
The question, Christelle, is noble gases, just to confirm the group they fall into, and also how they interact with other elements. Are they unreactive or hardly react with other elements, or because of their their energy levels or electron shells.
Okay, and noble gases are the last column, the column 18. Yeah, that is their group. Historically, they don't react with the other element. That is what is known now. They don't react with the other element because their outmost electron shell is saturated. So they don't have any free electron to react with the other element.
All right, thank you, Christelle.
Yes.
Lusango, you have your hand up. Do you want to expand on this, or do you have another question?
I thought the question was asking what are the uses of those noble gases since they don't react in any reactions. So most noble gases, as Miss has said, they don't react since the valency shells are full. So they don't have much uses in the chemical industry. But some of the noble gases, such as neon, are also used in neon lights. You can see them in cities such as Japan, or if you know one of those glow sticks or those necklace-like things that glow in the dark. Those are made of noble that are called neon. So they may not have much chemical use, but we do use them one way or another.
100%.
And I can say it not like that because they don't react with other elements that they are useless or we don't use them. We can use them as they are, and we also use them in some activity or some reaction where we want to like to stop the reactivity. And I don't know if it's mostly used in the refining of metals. So I don't remember which one exactly. Must be the helium or argon that is used in the aluminum process, and we use them where we want to provide like to stop the chemical reactivity.
Helium baths. Yeah, I've heard of that. Nice.
Yeah.
That's really good. Thanks for that. I didn't know that. Nice. Yeah. And
everyone is learning here.
Yes. And the last question was, why do balloons float to the sky?
Someone had an answer in the chat. I can't remember who tried to answer that question. If you've just written a response to that question about balloons floating in the sky, please put your hand up. Pudluvuga, do you see who wrote that that comment?
Lindy Sipo has her hand up.
All right, Lindy Sipo.
Balloons float in the sky because some balloons are filled with helium, and helium is less dense than air we have here on the ground, which is mostly like oxygen and carbon dioxide and stuff. So helium, yeah, is less dense because it has less mass. Yeah. So it will try to float up like higher into the atmosphere because air here is like dense and stuff. So yeah.
Exactly. That is as simple as that. And as simple as that, it's not like some balloon. When you see a balloon floating in the air, be sure that is filled with the helium. That is the element that is lighter than the air. Because in the air, we have so many elements. We have oxides, hydrogen, and with helium itself in the balloon, make it float in the air. That is simple.
100%. 100%. That's perfect. That's perfect. That is really good, guys. Well, that comes to the end of us. So thank you very much for joining us. You've made us feel like science is indeed cool, which we enjoy it, and we'll keep unpacking it, keep keeping it fascinated, keep the curiosity, and that's what makes us us. So thank you so much for having us. We truly appreciate it.
Oh, wow. Thank you so much, Ms. Michelle. Thank you so much, Christelle. We truly appreciate it. I think you really just, I don't know, unlocked the idea that the periodic table is like an abstract thing. You've really made it so beautifully practical for our FGLers, and I'm sure every single one of them appreciates it. Maybe, oh yes, you did say we are able to share this presentation with the FGLers?
Mm-hmm. Absolutely.
Yes.
Happy to
Okay. Fantastic, fantastic. Well, thank you so much. Be safe out in the UK. Says Christelle, be safe out in Uganda. And we are sure that we're going to connect with you sometime very soon. You've given us really some beautiful insights. We truly appreciate it.
Thank you.
All right, FGLers, that is unpacking, unlocking the magic of the periodic table, and hopefully really making sure that we simplify some of the elements of the periodic table, make it more practical, and hopefully now you're able to retain and have that stay in your memory for a longer time, and make sure that it's just a basic foundation that you can fall back in as you continue to navigate the world of physics and science. We have